in the total absence of rewards from the environment. It turns out it's not as crazy as it sounds, and that's precisely what they demonstrate in this paper, Curiosity-Driven Exploration by Self-Supervised Prediction. Now, before we go any further, I have to give a shameless plug. This is the central paper of my new course, Curiosity-Driven Deep Reinforcement Learning, on sale at Udemy right now. It just dropped yesterday, so I have an introductory sale of $9.99. After this, it goes up in price forever. I'll never sell it for $10 again, at least willingly. If Udemy does it, then I can't stop them, but I'll never offer it for $10 again. But anyway, shameless plugging aside, today I'm going to give you a kind of stripped down version of this. I'm going to show you the essence of the ICM algorithm, and we're going to code it up and show that you can actually get good performance in the cartpole environment without any rewards. So in the paper, they demonstrate this using two different environments. They use the Super Mario Brothers environment, pretty cool, as well as something called VizDoom, which is a sort of like Doom environment in which the agent navigates a labyrinth with Doom textures. There's no enemies or anything like that. We're not going to use VizDoom. We don't use it in the course. We use something called Mini World, which is very similar but has better computational performance. And of course, we don't use Mario Bros. Because Nintendo is very, very cagey about people using their intellectual property, and I don't want to get a cease and desist letter from a $50 billion legal team. So what we're going to do here for YouTube is show this in the cartpole environment. And what are we going to show? We're going to show that we can actually get learning without rewards. So how does that work? So ICM is a bolt-on module for an on-policy learning method. Really, it can be used for anything, but they use A3C, which is an on-policy learning method. This module just bolts right in. So it works like so. This diagram here encapsulates the essence of ICM. So the basic idea is here on the left we have our generic Markov decision process where you feed some state into a policy, it generates an action, you take that action, you get an intrinsic as well as extrinsic reward, where that intrinsic reward comes from the ICM module. That causes the state to transition to a new state at time t+1 that's fed into the policy, giving a new reward, and so on and so forth. All this information is fed into the Intrinsic Curiosity Module, which is shown in the diagram on the right. Now, really, it's comprised of three different components. So in the paper, they use pixel space types of environments. So they're navigating from pixels. So in Super Mario Brothers, it's obviously the pixels from the video game. And in the VizDoom environment, it's a picture of the labyrinth. So the idea is that you don't want to use the pixel space representation directly because a lot of things can change in the image that the agent itself is not directly controlling. And the curiosity reward is directly in proportion to the agent's inability, that is, its lack of ability to predict the resulting state. So the less an agent knows about the environment, the larger reward you give it, thus giving it greater incentive to learn more about that environment. As the agent learns more and more about the environment, that curiosity reward diminishes. Now, the problem with pixels is a bunch of stuff is changing that the agent has no power over, and in fact it may be totally random, right? You could have noise in the image, you could have leaves moving in the breeze, which is a fundamentally stochastic process as far as the agent is concerned, and so it'll receive a large reward just by staring at the leaves moving in the breeze, which is pathological behavior. It's not something we want. So their solution to this is to move into a feature space using a convolutional neural network as a sort of feature extractor, where the final layer of the convolutional network is flattened and passed into a linear layer. So the idea is you pass in the pixel representations for the state at time t and t+1, and it goes through the convolutional neural network and comes out as a feature vector phi. Now, we have two different models here. You have the forward model that attempts to predict the forward dynamics of the system. What that means specifically is, given some state at time t and the action the agent takes, what will be the resulting state? That is learning how your actions affect the environment. The inverse model attempts to answer the inverse question. Given two successive states, what was the action the agent took to cause that transition? And so you have these two different models that play together to learn the dynamics of the system. This reward here, intrinsic reward, if you follow the arrows, is related to this phi hat. That is the feature vector generated by the forward model. That's the predicted feature vector of the resulting state. And that's compared to the actual feature vector of the resulting state. And so the difference between those two will give you a type of intrinsic reward. That intrinsic reward is then fed back into the policy, which in this case will be the actor component of an actor critic algorithm, and that is used to help the agent maximize that intrinsic curiosity reward over time. Now, for our stripped out example, we are not going to handle pixel space representations. Of course, in the course I show you how to do that. I show you how to modify the OpenAI GEMS Atari library to facilitate that. But here we're going to deal with a stripped down version in the cartpole environment. So we're just going to have input vectors, which, if you remember, is a 4 vector in the cartpole environment, and it's going to attempt to predict those 4 vectors using the forward model, and then attempt to predict actions using the inverse model. So that is the basic idea behind it. We can take a quick look at some of the results from the paper. They do one experiment where they compare the degree of reward sparsity. Of course, reward sparsity meaning how likely the agent is to receive a reward. So this is for the VizDoom environment where the agent has to run through a labyrinth, and if it only receives a reward for finding the exit. So the idea here is they're comparing varying degrees of reward sparsity. So the dense reward setting means it spawns pretty close. Some of the time it'll spawn very close to the exit, and so it's more likely to receive a reward. And then the sparse and very sparse reward settings, they spawn it further away from the reward. So if you take a look, the orange plot, which is the full ICM algorithm, outperforms in pretty much all cases. So in the very dense, very sparse reward case, A3C and the ICM plus pixels algorithm fails completely. So A3C can't handle it, and neither can the ICM plus pixels, that is without using the feature space representation. So this is a pretty clear demonstration that it's well suited for environments with very sparse rewards. Another interesting plot or table is the performance in the Doom world. So here on the left in the green shaded regions, you can see its exploration achieved using just intrinsic rewards. So it manages to cover a fair amount of the level. And then the question is, well, how does that compare to a totally random agent? And that is answered in the final 2 plots on the right, where it just manages to make it through a couple of rooms by random movement. So it does show that at the very least, the intrinsic curiosity reward alone beats out a purely random agent. And they drive this point home in this data table down here, where they do a few different experiments. They'll train an agent in Mario level 1 with just curiosity rewards, no extrinsic rewards. And then they can train it in levels 2 and 3, or test it in 2 or 3, as in just run it as is, or they can fine tune it with extrinsic rewards. So turn on the extrinsic rewards from the environment and see how it performs. What's really interesting is that in level 3, we see that when you run it as is, meaning you train it on level 1 with no extrinsic rewards and just let it loose on level 3 and see how it does, it makes it 319.3 units of distance, whatever unit of distance they use. Whereas if you train it from scratch for a total of 5 million pixels in level 3 using the intrinsic rewards only, you only get a score of 42. So a factor of pretty much 8 or 9 better using the training on level 1 and then deploying in level 3. So it's learning something generalizable in level 1 that it can use in level 3. Pretty fascinating stuff, and in fact it does better than fine-tuning, which is kind of interesting to me. All that said, now we're going to go and code up our own version. So what we're going to do is we're going to code up an A3C agent, which we've done before on the channel, but this version is slightly different. I've tweaked my implementation a little bit for this course, and we're going to implement the ICM module as well, and we're going to test all of this in the cartpole environment, where we are going to do away with this feature extractor from the diagram. Here we're just going to deal in the actual vector space of the cartpole environment. So it's a 4 vector, and we're going to be dealing with predictions and in that particular space instead of the underlying feature space. So here we are in our terminal. Let's start with our actual actor critic agent, and we're going to need a whole bunch of imports. We'll need NumPy, we'll need Torch, and we're going to need our categorical distribution. That, of course, is used for environments with discrete action spaces. So our actor critic is going to take some input dims, number of actions, a gamma of 0.99, and a tau of 0.98. Now in the course I also show you generalized advantage estimation. I give a brief mini lecture on that. I encourage you to check out the paper. It's a really good paper, but that parameter tau is the lambda from the paper. I call it tau because lambda is a reserved keyword in Python, so I just renamed it to tau. Now our network will need an input layer, and that'll take 256, an input and translate that into 256, and then our dense layer. Now keep in mind this is the A3C agent, not the ICM, so this is the actual on-policy learning algorithm to generate the policy pi, and then ICM is a bolt-on module which we will code up next. Now we're going to need a LSTM type layer. I'm going to use a gated recurrent unit. I found pretty good results with that, and it has a little bit less complexity than the LSTM. Our policy is just a linear layer. And our value function is, of course, also a linear layer. So now we need our forward propagation. That'll take a state as input as well as a hidden state for our GRU. Now here I'm assuming that state is already a PyTorch tensor, and we say f.relu self.dense x and then hx then we want to pass that hidden state through our PyEnv layer to get our logits for our policy as well as our value function. And then typically I would use a choose action function, but here I'm just going to roll choose action into the forward function, the feed forward. So I'm going to get the actual probability distribution. It's going to be a softmax activation on the first dimension. We have our distribution, our action, and then we need our log prob. Then we return what we need. We say return action, numpy, 0v log prob, and the hidden state. Now we need a couple functions to handle the calculation of the loss. If you go back and look at the A3C paper, they use a sort of kind of low tier estimation of the advantage function. They call it the R in the paper. We're going to calculate that first, and then we're going to do our generalized advantage estimate for the actual generalized advantage for use of the calculation of the loss for our actor. So we have this function calc R. It's going to take a done flag, set of rewards, and a set of values. Now rewards and values are stored as lists of tensors, so we have to convert that list of tensors into a single tensor and squeeze it because we don't want t time steps by 1. There are two possibilities here. We could have either a batch of states or a single state, so the A3C algorithm gets triggered every capital T time steps or when the episode ends. So we have to account for both possibilities, and there may be a better way of doing this, but this is how I got it working. So if we have a batch of states, then the length of the values.size tensor will be 1. In which case R is just going to be the last element of the value array, a value tensor, multiplied by 1 minus int of done, because the value of the terminal state is identically 0. So if the length of the values dot size tensor is 0, then we're dealing with a single state. So it's just r equals values times 1 minus int of done. So now we have to calculate the returns at each time step of our sequence. So we have this list batch return, and we're going to iterate backwards over our rewards. We're going to say r equals reward plus self.gamma times r. And then we have to return it, or excuse me, reverse it, and convert it to a tensor. And then dtype t float. And then return. Okay, so this quantity r will be used for the calculation of our critic loss. Kind of speeding through this because I don't want this to be a 2-hour video. But again, you can read the paper. It's a pretty well-written paper. There's nothing super mysterious about it. So our loss function is going to take quite a few inputs. We need our new states, our hidden state, our terminal flag, rewards, values, log probs, and an intrinsic reward. So this code is going to be general enough that we can use it for vanilla A3C as well as ICM. So if we're supplying an intrinsic reward, then we want to add the reward from our ICM, but we want to convert that to NumPy array because it's a PyTorch tensor, whereas rewards is a list of floating point values. Next thing we have to handle is our generalized advantage estimate. I go over this in more detail in the course. You can look at the paper. The paper is actually really well written as well. You only need a couple equations from it, but the basic idea is we need the value function for the state after our horizon, one step after our horizon. And that state can be done, in which case we want to use 0. Otherwise, we want to forward propagate the new states and get the first element because the others are other stuff that isn't the value function. If you look up here, so the value function is the 0, 1 element. So that's why we're getting the 1. That's where that comes from. Now we append that. We want to detach it. And then we say values equals t.cat values. Same thing we had to do in the calc r function. Dot squeeze. Our log probs are also a list of PyTorch tensors, so we want to concatenate those and then convert our rewards to a PyTorch tensor. Then we have our delta t from the paper, and that is just the reward plus gamma multiplied by the state at time t plus 1, and then subtracting all the state at time t. So delta t is rewards plus self.gamma times values of 1 onward minus values up to -1. So that's a vectorized implementation. Now we need our generalized advantage estimate calculation. So for t in range, number of steps, so there's going to be an advantage for each time step in our sequence. So what this is going to be is a batch of states, capital T in length, something like 20, let's say. And so we have an advantage for each of those 20 time steps. And the advantage at each time step is proportional to a sum of all the rewards that follow, and multiplied by this delta function. So you have to take 2 loops, so 1 for each step in that sequence, and then the inner loop goes from that step onward to the end. So we're going to take the delta sub t plus k multiplied by a gamma tau to the k power, and then set the GAE at that time step equal to, or plus that temp. Then at the end, convert generalized advantage estimate to a PyTorch tensor. Now all we have to do is calculate our losses. Our actor loss is the negative log probs multiplied by GAE dot sum. Let me be super pedantic and put that negative sign at the end, or at the beginning. Our entropy loss, in the paper they use entropy regularization, is negative log probs times t dot exponential of log probs dot sum, and our critic loss equals the mean squared error loss of values 1 up to -1, because remember we stuck on the value function for the state that occurs after the capital T time step, and we want to subtract off those returns. Now I have this squeeze here because sometimes you'll be dealing with a single state and then you get a shape. It's easier to type. You get shape capital T versus like a single scalar. So I add in that squeeze function to take care of that. Then our total loss is just our actor loss plus the critic loss minus 0.01 times our entropy loss. And that comes from the paper. And of course we want to return that total loss. And it's unhappy because I have a couple blank lines. Undefined name returns. Oh yeah, well hey, that's a problem. So we have to calculate our R. So can't believe I forgot that. Calc R done, rewards and values. There we go. So now let's see what it's unhappy about. Some missing white space. So I updated my Vim installation, and it is pretty particular. Whatever, I don't care. It's unhappy about my indentation. It has PEP 8 style awards. PEP 8 style warnings. That's kind of annoying. So let's do a right quit. Oh, I have 2 of those. Let's fix that. Which line was that? Oh, right there, right in the initializer. Okay. Oh my gosh. Trailing white space, whatever, you'll live. Okay, so now we have our actor critic. Now let's move on to the difficult business of our ICM. Now remember, the ICM here is slightly different than in the paper because we're doing away with that feature space encoding. And we're doing away with it because it doesn't make a whole lot of sense to have a feature space encoding in the case of the cartpole environment. It's a simple enough environment that we don't really need it. We're going to need our input dims, a number of actions. Now, one thing I didn't discuss is the loss functions. So in the inverse model, you want to predict the action the agent took to cause the state to transition from state at time t to the state at time t plus 1. So you're comparing an integer, a multi-class problem, right? It can be action 0 or 1 since it's a binary action system in the case of the cartpole, versus an actual label, the actual action the agent took. So that is just a multi-class classification problem. So that is just a cross entropy loss between the predicted action and the actual action the agent took. Then in the paper they tell you that the loss for the forward model is just the mean squared error basically between the predicted state at time t plus 1 and the actual state at time t plus 1. So we're going to have 2 different losses for this particular model. And then our intrinsic curiosity is basically the same thing as a loss forward model, except you have some multiplicative constants. So one of those multiplicative constants is a parameter from the paper they also call lambda. They use lambda again, and that is a parameter that you use to weight the relevance of the intrinsic reward relative to the extrinsic reward. Now in this case, we're not going to be using any extrinsic rewards, and so I'm going to set the lambda to 1, or the alpha in this case. That is just because we don't want it relative to anything. We want the full intrinsic reward. We don't want it to be a really small number, so we're not going to multiply by 0.1. That's what they use in the paper, is 0.1. This beta has to do with the loss for our our inverse and forward model. So you're going to have a beta multiplied by the loss of the, let me make sure I get this right, of the forward model, and then 1 minus beta multiplied by the loss of the inverse model. So that is where the beta comes from. It's just a hyperparameter from the paper. Now we need our models. So the inverse model takes 2 successive states and tries to predict what action. So our inputs is going to be 4 times 2, because the input vector from the cartpole environment has 4 elements, and we're going to have 2 of them. That's going to feed into a layer with 256 units. And the logits from our policy is what we want to predict, and that takes that 256 elements and dumps it out into something with number of actions. Then the forward model takes a state and action and says, what is the resulting state? So the inputs are 4 plus 1, so 4 from the environment plus 1 action. That feeds into a layer with 256 units. The new state that we output should have shape input dims. Really, this is just a 4. Let me just hard code it here as well, because we know it for the cartpole environment. I know somebody's going to ask about that, so let me put a comment in there. Then we need our device. Oh, you know what? I think I forgot that for the actor critic model. Now we need our feed forward. That's going to take a state, new state, and action as input. So our inverse we have to concatenate a state and action and pass it through the inverse layer, then activate it with an LU activation. That's exponential linear. Cell.py log its. So then we have our inverse layer. Now we need our forward model. We have to take our action and reshape it. So the reason is that we want to go from t to t by 1, where we have t time steps in our batch. I'm missing a parenthesis there. So our forward input, concat state and action along the first dimension. Pass that through our forward input, activate it, and get a new state out the other end. Return our PyLogits and new state. Then our loss function takes the state, new state, and action as input. Basically, we're just going to feed all this stuff through our network. We're going to say state, tensor, state, float. We don't need brackets here because state is already a list of states. Really, I could make this plural, but I'm going to be lazy for now and not do that. And then new state. pass those through our network, get the values out. Then our inverse loss is a cross entropy loss, because in general this will have more than 2 actions. So our inverse loss is then 1 minus self.beta times inverse loss between pi log its action to t.long. And we need that to torch.long. That's kind of what it expects for the label. It's a long type, so whatever, that's how PyTorch does it. So then our forward loss, mean squared error loss, so it's the loss, the mean squared error between our predicted new state and actual new state. Then our intrinsic reward is alpha multiplied by state minus new state squared mean along the first dimension. That dim equals 1 is very, very important. If you omit that, it will take the mean across all dimensions and you just get a single number. And that is totally not useful because the curiosity reward should be associated with each state. So you have to take the mean across that first dimension, which is the number of states. Intrinsic reward, Li and Lf. Okay, so that, do I have a warning here of some kind? Oh gosh, end of file and multi-line statement. So I've neglected a parenthesis somewhere. We want to concatenate along that dimension. Yeah, that got rid of the warning. Okay. Okay, so that is our ICM. Now we have a whole bunch of other stuff we have to code around it. So we have a whole lot of infrastructure associated with the A3C. We have a batch memory. We have the functionality to parallelize our environments and agents. And we have a SharedAdam optimizer where we share the optimizer between the agents. So let's start with the easiest one. And we don't need any imports for this. We're going to do the simplest possible thing. So we're going to have states, actions, rewards, and new states, values, and log props. So we're going to need to restore a transition. Then we need a function to clear our memory. You know what? Let's be lazy. Let's yank this and paste here. All right. Then we can sample our memory. And then return pretty much everything. All right, now it's happy. Okay, so that's it for our memory. Now let's do our SharedAdam optimizer. We'll need torch. Now this derives from torch.optim.atom, and I did not come up with this and I cite this in the course. I give credit to the appropriate author. I got this from Morvan Joe's GitHub. There isn't a whole lot of documentation available on this, so I ended up finding somebody else's solution and totally lifting it. Check out his tutorial, his code on A3C. He has a different take on it, but it works, and it's always good to see other people's stuff. So we're going to be optimizing our params. So these are our default parameters. Then we're going to iterate over our parameter groups and then iterate over parameters in each group. We need exponential average. Note the underscore at the end of memory. And that is all we need there. Okay, so we have our memory SharedAdam. Now we need our parallel environment implementation. We'll need torch multiprocessing. No, that's not right. So that the torch multiprocessing version is identical to the underlying Python implementation. It's just PyTorch's version of it. We're going to need an actor critic. We're going to need ICM. The worker function is what handles all of the main functionality. It's really our main loop of the program, but it gets called by the multiprocessing process function, which we're going to invoke here in a second. We haven't written that yet. So we're going to take an environment ID, input shape, number of actions, ICM as a Boolean, whether or not we want to use the ICM algorithm, and the number of threads for default. If you have 8 threads, I would definitely recommend using them, but I wouldn't recommend using all your threads. You don't want to bog down your system training something silly. So use a subset of your threads. I've got 16, so I'll use 12 for this demonstration. I'm just defaulting it to 8 here. First thing I want to do is name all of my threads just for bookkeeping purposes. And then define global actor critics and global ICMs. So we're going to tell the software that we want to share the memory of our global agent amongst all the local agents. That's the basic idea behind A3C, is that you're going to have a whole bunch of independent agents in their own thread interacting with their own environments. They're going to do their own learning and then upload their learning to the global megamind, the global actor critic. And I don't need a learning rate there. So if we're not doing ICM, then don't do ICM. Now we have to define our processes. And the target is the function that we're going to call for each individual thread. And then we have to specify the arguments for that function. Is it going to complain about under-indenting? Yeah, it is, of course. And then this says is over-indented. There we go. All right, now we have to start and join our threads. Say p.join or p and self.ps. Okay, so that is it for the parallel portion of our implementation. So this handles firing up all of your threads. That's what we do with start. And then join, basically I don't think we really need it, but the idea is that it won't leave a zombie thread running if the main thread exits for some reason. I haven't seen it be an issue here, but I've included it for best practices. So that is our parallel environment. Now we can write the worker function, which is the bulk of our code. It's pretty much our main loop. And we have a whole slew of imports here. We have gym, numpy, torch, we'll need actor critic because each thread gets its own individual actor critic. We'll also need an ICM. We'll need a memory. We'll also have our PlotLearning curve function. I can write that at the end. So our worker function takes the name, input shape, number of actions, global agent, global ICM optimizer, ICM optimizer, environment ID, number of threads, and our ICM. We'll default that to false. We'll need a maximum number of steps, 20. We'll need a local agent. So if we're using ICM, then algo is just going to be a string for printing debug information to the terminal, as well as saving our plot at the end. ICM, we're not going to need it, sorry. Intrinsic reward. So we're going to print the intrinsic reward the agent receives to the terminal. If we're not doing ICM, then we don't really need an intrinsic reward, but we'll still have to print something. So it'll just be identically 0. Each agent gets its own memory, its own environment. We're going to need a bunch of variables, total time steps taken, so you can see how many time steps we've been training, the current episode, a scores list, average score. So we're going to play a total of 1,000 episodes. I've gone as high as 10,000. It doesn't fundamentally change the results. It's not like the agent starts to learn after 1,000. So 1,000 will be sufficient. Then we have to do our main loops. We say while episode less than max episodes, reset your environment. Make your hidden state for the actor critic. We'll need a score for the episode, a terminal flag, and the number of steps taken within the episode, because every 20 steps within the episode we want to execute the learning function. So we play each episode. We want to convert our observation array into a PyTorch tensor. Feed forward our state and hidden state through the local agent to get the action we want to take, value for that state, log prop that action and the hidden state back. Take your action, increment your total time steps, increment your episode steps, increase your score. When we turn off the intrinsic reward, we're going to set reward to 0 here, because we still want to know the actual points the agent scored, but we don't want the agent to know how many points it scored. So action reward observation underscore value and log prob, and then set the current state to the new state. If our episode steps modulus tmax is 0, when we're done, then it's time to learn. So we'll sample our memory. If we're doing ICM, then we want to calculate our loss according to our local ICM. And then we want to say the loss due to the, according to the actor critic, our A3C agent. Values, log probs, intrinsic reward. So I just realized the way I coded this up, the intrinsic reward will be, I guess it doesn't really matter adding a 0 for the intrinsic reward. It's a bit of an oversight. I don't think it'll break anything. I mean, I know it works, but it's not optimal. So I would encourage you to go back and rewrite this to where, yeah, if you think about it, you'll see the bug. It's not a bug, it's a feature. So we want to 0 our gradient. We have to detach this hidden state. Reason being, it gives us a reward about trying to back propagate through the graph twice. So that's a problem. So if we're using ICM, go ahead and 0 the gradient and back propagate your loss. Either way, back propagate the loss from the actor critic agent, and then clip your gradients. They do that in the paper, just kind of a standard practice. Using the value 40, I had to look at their code to find that they don't specify what value they use in the paper. That's the A3C paper, that is. Next, we want to take our gradients from our local agent and upload them to the global agent. step our optimizer, and load our state dictionaries. So basically download the learning from the global agent. So then if we're doing ICM, we basically want to do the same thing for the ICM agent. So we say local ICM parameters Then we want to step our optimizer and do the same thing with downloading the parameters. And then at the end of each learning step, we want to clear our memory. And let me double check to make sure that's the end of the episode and not the end of all episodes. Yep. So at the end of each episode, we want some debug information to print out to the terminal. So we'll say if name equals 1. So I'm only going to print debug information for the first agent. We're going to append our score to the scores array. Take its average, the previous 100 games, and print some stuff to the terminal. Hang on, I got a cat wanting in the room. All right, so we want to print our algorithm, episode number, how many threads we're doing, how many steps we've taken, the score for the episode, the intrinsic reward, which for A through C obviously is 0, average score of the previous 100 games, we want the algo, episode name, number of threads, T steps 20 divided by 1,000,000, the score. Oh, good grief, I'm gonna have to that score. It's gonna really complain about the unindent there. Increment our episode counter by 1, and at the end of all the episodes, for the first agent, we want to print our or plot our graph. Our x-axis, our file name. We'll start with rewards, cartpole.png. And we'll plot that learning curve. Hey, it helps to indent stuff, doesn't it? Okay. So let's see if it's unhappy about something. I have a feeling it might be, this end of file and multi-line statement stuff again. Okay, let's see where I did that. Oh, of course, it's right here. There we go. Is it? Is it not? Oh, blank line. There we go. All right, now it's happy. Okay, we're almost there, I promise. So we have two things. We have the main function that's just going to call the parallel environment, and then we have our plot learning curve. Let's handle that, because that's pretty easy as well. So we need matplotlib and numpy. So our plot learning curve function, I've never actually written this on camera. That's kind of funny. So our running average mean of scores of the max 0I minus 100. It's going to complain about that, isn't it? Up to I plus 1. All right. Now we need our main function. So this is pretty straightforward. We have to import OS because we have to tell the operating system we want to dictate the number of threads we're going to use. We have to set our multiprocessing start method. And we need a parallel environment. We have to tell it we want to use, we want to specify the number of threads. We have to set our start method. I'm going to use spawn. Reason being, spawn seems to be the most universally accepted method. Some of you are running Windows. If I use fork server, then it's not going to work on Windows. You can also use, I believe, just fork. I think there's 3 different options, but spawn is the only one that'll run on all 3 operating systems, even though it is the slowest. Our environment ID is cartpole v0. I'm going to run with 12 threads. The cartpole environment has 2 actions. We're going to put shape as a 4 vector. We need to call our environment ID constructor. And we're going to start with just A3C. Okay. Oh, of course, I forgot my double underscore here. Okay, moment of truth. Let's see how many mistakes I made. Torch out handout function. Okay, so that's an actor critic. It's function null. Sure you guys caught that. Enough of your trailing white space lies. I don't care. Now it runs straight away. Okay, so I'm gonna let that run for a few minutes and I'll show you the results. Okay, it's only been a couple minutes, so you can't really see the average score, but you can see very clearly that it's scoring 200 points pretty much each episode. Now, I'm not going to let this run the full 1,000 because that's going to take longer than is necessary. The point here is I'm validating that our A3C agent works. We didn't make a mistake. Always want to make sure the A3C agent works before you add on the ICM. So let's go ahead and stop that. Then we're going to go to our worker file and come down here and uncomment this line. So now we're going to turn off our extrinsic rewards, and I will let this run 1,000 games. Insert no rewards so you can see the performance. So I have turned off the rewards and we want to see how it's going to do. I already know how it's going to do, but you can probably already guess as well. But let's verify that with no rewards, we don't get any points. Okay, now that's going to run, and I'll leave it run the full 1,000. We'll be back shortly. Okay, so this finished, and you can see that the average scores are in the mid-20s, so rather low to mid-20s, so not very good. It actually does better than one might expect. You know, it doesn't get a score of 10, doesn't almost instantly flop over, but still, it obviously did not learn its lesson. So now we can go to main and change ICM to true. Let me double check the worker file. So it is going to say fname equals algo. All right. So now we can try with the ICM, and that'll take a little bit longer to run because ICM is you're adding on a whole extra network. So let's go ahead and, oh, of course I do have an error. It says, which line is that? Cannot assign module before module init call. That's interesting. So let's take a look at our ICM. Oh, I forgot the call to a super constructor for one. I think I got that backward. All right. There we go, of course. All right, so this will take a little while to run. So I'm going to come back when it is finished, and then we're going to look over the results. Okay, so that took a few minutes to run. It didn't take as long as I thought it would, actually. So if you scroll back over the rewards, you can see that it does get scores around the 80s on average, with some episodes hitting the 100 or so mark. Now what's interesting is that toward the end, this intrinsic reward really drops off to 0. If you scroll up, in particular, you can see sometimes it's as large as 0.18. I don't know what the largest one I've seen. I haven't scrolled through all these numbers, but you do see quite a few relatively large numbers. And the idea here is that the intrinsic reward should be large for states that the agent has difficulty predicting. In other words, states that it hasn't visited before. That's why the intrinsic reward causes it to do some exploration. Now, the fact that it falls off is actually a bit of a problem. And it's a problem that gets addressed later on in a paper around an algorithm called Never Give Up. It's something I'm looking into now, but it's a different take on curiosity, where it causes the agent to keep exploring even when it gets bored, effectively. It never gives up, never gets bored. So if we take a look at the plot here, you can see that it does achieve a pretty high score, a little over 100. Now, it doesn't totally solve the environment, but it does manage to get a relatively high score. Now, what's interesting here is that we're not quite using it in the way in which it was designed. So my purpose here is simply to show you that the ICM works, and that it does get better scores than A3C, not that it's stable necessarily. The purpose of the let's say the intrinsic curiosity is to generate skills that can be applied to new novel contexts. We can't really apply the learning from the cartpole environment to any other environment because there aren't other environments with similar inputs and similar action spaces. So this isn't as applicable as the underlying feature space in the paper, but it's to give you an idea and a feel for intrinsic curiosity. You can check out the code on my GitHub. Please buy the course if you want to support the channel. Of course, if you don't have the money, that's perfectly fine. I make all this available for free. You can read the paper on your own, take a look at my code on the GitHub, and that'll give you a really good idea of what's going on. All that said, I hope this was helpful for you. If you've made it this far, please consider giving a subscribe, hit that like button, drop a comment down below, and I'll see you in the next video.